The first question of theory assignment. Okay. Just a second. I don't remember what question I asked you. Okay, where did I go? Oh, this one. Okay. Yeah. So this is like, okay, there are these two brothers who are in like different cities. Okay, and so you have to formulate a plan so that they can meet up. Okay, they can meet up in any of the other cities also. Okay, and there's a time to go for each of them. There's a time to go from one city to the other, and that is the same for each of the brothers. Okay, so time to go from X to Y is this TXY. And so the thing is, like, when you make a plan, you have to ensure that, if the first brother decides to go from like A to B, and the second brother decides to go from P to Q, if that is an intermediate stretch, then he cannot, like, if the first brother reaches B first, he cannot proceed to the next action immediately. He has to wait till the other brother also reaches, from P to Q. Okay, if they are in that stage, and then the next action they can take only after both of them have reached that intermediate destination. Right? Was this the confusion, or
Yeah,
Tushar?
ma'am. Actually, like the persons do the persons know like beforehand where they're going next, next
Yes.
destination.
So this is what you have to design. So your plan should be to decide a path for them, right? You only know that the starting point for both of these people, that is C1 and C2. And the destination also can be anything. It can be any of the cities. And yeah, even the path, the outcome of this plan should be a path for one brother, for Amar, and another path for Akbar. So of course, both these have to end at the same point, right? Because that's where they will meet, right?
Okay.
It's clear, Tushar?
Yes, ma'am.
I have a doubt in the same, ma'am. Does this
Yeah.
path has to be shortest, means according to in the uh, respect of time? Does it have to be fast?
Yeah, as quick as possible. Yes.
Oh,
Right. So by now you must know that it will all depend on the way you formulate it. So to get the quickest path possible, you have to use some notion of costs, so that if you apply any of the algorithms, like maybe a BFS, if you do, it will give you the shortest path. So the main catch here is in how you formulate it. Right? It's a search problem. You have to formulate the transition costs properly. That's the main idea. Okay, is this clear?
yes, ma'am.
Who asked after Deep, right? It's clear, right, Deep?
Yes, ma'am.
Okay, cool. Yeah, so I hope this is clear to all. So maybe let's go back to the MDP topic. Okay. So yeah, I've started the recording. So good. All right. So where were we? Yesterday we were looking at how you evaluate some policies. So we saw an example of this where we were given a fixed policy, where a policy was a mapping from a state to an action, right? And we saw how you can get the value of each of these states under the policy by solving a set of equations. Okay. And so then we evaluated this for two policies, and we saw that you cannot say always that one policy is better than the other. For it could be that the case that one policy is better for one state, but whereas some other policy is better for another state. So that's an example which nicely got illustrated when we computed for these two policies, pi 1 and pi 2. So for VC, we had pi 2 was better, but for the warm state, we had pi 1 was a better policy. Okay. And so one question for you all. So what is the number of policies possible? Right. You can define any kind of policy, right? From a state to an action. For each state, you have to take some action. So what is the total number of policies that you can have?
Maybe the combination of states we have, like all PNs permutations of that. Yeah.
Yes, exactly. So what is that number? So if S is the number of states and A is,
And
maybe
your
you
screen
take,
is not visible.
oh, it's not visible. I didn't share my screen, so sorry. Oh, I was explaining that assignment also without sharing that. Okay. Okay, I'd open the assignment question, but anyway, never mind. Okay, so thanks for pointing it out. So we had these policies, right? Pi 1, pi 2. We saw two example policies. So what is the total number of policies possible? If you have S states and A is the number of actions, and assume that all actions are permitted at every state, right? So what is the total number of policies that you can have?
Maybe S power A.
S power A,
No, ma'am. Sorry, A
A to the
power S.
power s.
A
A
to the
power
power. Sorry. Yeah.
S, right? Yeah, because so for state S1, you can have A actions. For state S2, you can have A number of actions, like that. So all the way for, S, whatever this number, right? Uh, this cardinality of S for that state also, you can have this many actions. So this product is the total number of policies. So the number of policies is typically quite large, like because it's exponential in the number of states. So you don't want to evaluate each of the policies to get what could be the best. And so that's why we started going into, some other notions, the value of the optimal policy. And I also told you that, between every pair of policies, I mean, every pair of policies may not be comparable, but it turns out that there is a best policy. Okay, so what do we mean by the best policy? So that's what we were defining yesterday. And we said that V star of S was the value of state S. If you start from S and you always take the best action. Okay, at every state, you take an action which gives you the best value. Okay, and similarly, Q star. So it was best understood with this tree. So you start from S, you will take an action which is best for you, which gives the best Q values. And in Q also, Q, of course, it's a random state. So there is no decision to be taken here. Okay, but one of these states are going to appear after this. So S prime appears, and once S prime appears, from there you're going to take the best action. So that's why the subsequent actions will affect the Q value of the states also. Okay, so that's why we called it Q star of SA and V star of S to denote the optimal value. And we saw these recursions. So these are the Bellman equations. So Bellman. Okay, so it's double L. So V star of S is out of all the possible actions, what is the best you could take? So max of Q star. And Q star is there is no action, so it's an expectation over all possible states you can reach. And then this was the value of subsequent thing. So RSA S dash was the first reward, and gamma times V star S dash was going further. This was the reward. Okay, so this is where we stopped, and I told you that this is, it's an example of dynamic programming that you would have seen in your algorithms class. Now, so this is the value of a state, okay, the optimal value of a state. Now, the optimal policy, pi star, let me just write it here itself. Okay. Okay, these are the Bellman equations. And based on this, you can get the optimal policy pi star. So what this is just over in this equation, what is the best action, right? So the action which gives you this value V star S, that is the policy. So that we'll call this as argmax. So it's the argument of, the set of all actions. And then the particular argument, the particular action which gives you the maximum value of Q star. Okay, so that's what this notation argmax means. Okay, so that is what we will define as the optimal policy. So this is the optimal policy. Okay, so have you seen this notation used earlier, this argmax, argmin? Have you come across this anywhere?
Yes, ma'am.
You've seen it. Okay, so that's fine. I just explained it in case you're not familiar with it. Okay, so yeah, so these are things now. We have these expressions, um, and we have to now somehow compute pi star. And of course, the way to do pi star, to compute pi star, is to compute the v stars, right? And so yeah, how do we do this? That's the next question. So if you observe these set of recursions, this is exactly what we did in expecting max, right? Do you recognize that? You start from a state S, you took some action which gave you the best, and the next was a random agent, and randomly one of these states came up, and then you took the best action, and then the random agent came, right? Is this clear that the connection with the expecting max? Right?
Yes, ma'am.
Yes. Yeah. So exactly what we are doing here is an expecting max computation. Now, there's some difference here. Can you tell me? Like, it's not very, though it is exactly an expecting max computation, but how do you really compute this? Right? There's some difference here. Are you able to spot the difference? Okay, where do you start from? Like, how did the expecting max computation start?
Bottom up.
Bottom, right? Like you always started at these terminal, you had some terminal states there, right? In the case of expecting max, you had these terminal nodes which you knew the utility, and then you kind of moved back and back. But here in this case of MDPs, the tree is always going to be an infinite tree, because you go up to infinite time steps. Okay, so yeah, so you don't have a base case, right? So yeah, what do you do, right? Do you see that? Do you understand this point?
Yes.
Yeah. Okay. So yeah. So do you have any thoughts on what we can do? Any ideas? Anybody? Okay, you've seen this idea before, right? Like about anything about assuming the tree is smaller or something like that. Can you do something with that point of mind?
We can stop at a selected depth and then use some function to get a value, like assumed value at that state.
Okay, yeah. So the idea is essentially that, but we are not going to, approximate the value anywhere. What we'll define is exactly this notion of truncating the time steps. Okay, so yeah, what one possible idea here is to say to think of how much more time you have ahead of you. Okay, so consider the hypothetical situation where the process is going to end in k more steps. Okay, so something like this. So vk star of s. So you define a value like this. So this is the value of state s, value of state s, assuming, if you have k more time steps. Okay, so it's an infinite process, but you are trying to cut it down and say that you have only k time steps left. And so what is the best value possible? You have k more time steps left. So value of status, if you have k more time steps left and you uh, behave optimally, and we behave optimally. Okay, so let's take an example. So if V star of 0, so if you have 0 time steps left, right? So you're already at the end of this MDP, at the end of the evaluation. If you had no time left, then what is the value you get? What's the possible value you can get?
Zero, because there will be no transitions.
Yes, no more transitions, no more actions to take. So this you can just define as 0 for every state. Okay. Now, if you have one more time step left, what would that be? So you have S, and you can take one action, and after this it's going to stop. So what is it? What can you tell? What is the best thing to do?
Maximum reward for one time step.
Yes, exactly, right. So choose the action which give you the best value in the next time step, right? So here, so it is what would come here. Of course, there's going to be a Q state also, right, which comes here, and then you will have one of the possible states which come out, right? So again, that's going to be a function of Q, but what would the value be?
QS, A, S dash.
Yeah, so you will also have an appropriate term, something like this, QSA, right? But anyway, let me just write it directly. So if you are in this state, in the Q state, what is the value you're going to get? We'll just write it directly instead of going to 2 steps. But yeah, what happens in this Q state? What is the value you will get from one action? I mean, from one move.
Summation of transition probability into
Yeah.
reward plus gamma times.
Yeah. So the reward of SAS plus gamma times what you got in this state, right? So this was V0. Okay, so gamma times V0 of S dash. And this is anyway, you know, it is 0. So it's ultimately only this term remains, R of SAS dash. Okay. So this is overall possible states. And so you take the max here. Okay, if you had just one time step left. What happens in the next time step? Let's just write one more. So this is like one more, right? So this was V naught here, and here you had V1, and maybe here you have V2. Okay, so there's going to be a Q, and maybe you come here. So what happens?
Maximum of overall actions, summation of TSA, and same.
Same thing, right? The only difference is instead of V0, you have a V1, right? So TSAS dash times the same quantity. I'll just write it here so that it's complete, and if somebody's a bit confused, you can just verify it. Okay. So this is summation over all S dash. Okay, so you keep on doing this. Okay, and so generally what you're going to have is at the k plus 1th time, if you had k steps, k plus 1 time steps left, what you're going to get is the same expression, but just that you use Vk. Okay, RSA S dash plus gamma times Vk of S dash. Okay, this is what is going to happen. And so it's like an iterative process, and at some point you will converge. Okay, and so that's the idea. So the proof that it converges, we're not going to do it here because it involves a little more concepts like things like contraction mappings and all that. So if you're going to do a course on reinforcement learning, a dedicated course in RL, at some point that would cover these proofs in more depth. But here we'll just see how to use it. Okay, and it converges. The intuitive idea is just that, you know, at every step of the iteration, these terms, VKs, right, those are going to get multiplied with gamma. So the only issue is that, you know, maybe you started off with V0 was a wrong value, perhaps. Okay, but finally, when you reach enough number of time steps, see that at k plus 1, you are scaling Vk by gamma. So in turn, it would end up scaling Vk minus 1 by gamma square, like that. So all the way it would scale V0 by gamma power k. Okay, so gamma is a value which is less than 1. So gamma power k is also going to be a very small quantity. So the bad values get scaled, like, if you do enough number of iterations, the ones that cause some issues, those get scaled by very small quantities. So it won't matter. Okay, that's the proof idea. But to write it mathematically, it requires some other concepts. Okay. All right. So we said how to compute V star. Now, at each of these steps, you can also compute pi star, right? Based on the value that you have so far. So, let's just write it here. So pi k plus 1 star, that can be just the argmax of this quantity, right? So argmax of A and whatever you've computed here. So what the idea is that you first compute V0 star and then you get pi 0 star based on the best value computed V0 star. Then you get V1 star using this, not using this, you already have V0. Yeah, so using V0 star, you compute V1 and then you get pi 1 star. But actually, you don't have to compute pi's at every point. I'm just telling you, like, just to understand what kind of intermediate policies you get. Okay, but really you don't have to do this step at all for the computations. Only in the end you decide that you're going to run this for some iterations, and at the end you can just do a pi star as argmax of basically this, whatever you computed with Vk plus 1. So basically the same quantity, RSA S prime plus gamma Vk plus 1 star of S. Okay, so all these have a star. Okay, I might have missed it. Yeah, V0 star. So what is going on here is that, so at level k plus 1, so let me say this as a state S. And what you're going to call here is, some action you take, and you'll reach a Q state, and that again goes to some other action. So Q's we marked as squares, and like that it goes on, right? So again there's a Q state, again there's another state. I need a huge board. Okay, so like this. So this is like Vk plus 1, and you're computing it using Vk. So there's a huge tree here, and this in turn calls Vk minus 1, like that. Okay, and all the way till finally you have the terminals. Okay, so the terminal is used in a different sense here. Okay, so up till V0. And what you have is the pi, the last value, pi k plus 1 star, is telling you based on these values, Vk plus 1, what is the best action you take. If you had a Vk plus 2 here, what would have been the best action? So it's as though you're computing that. Okay. Is this computation clear to you all? Are there any questions? Yeah. Tanuja, are you clear with?
Yeah, it's
Yes?
yes, ma'am.
Okay. Maybe let me ask some more people. Jaishika is clear. Right. Okay. Akshit. Akshit Garg is here. You type into me. It is clear. Okay. Kunjan's clear. Rishabh. Good. Okay. What about Himanshu? There are two Himanshus in this class, so what about both of you?
Yes, ma'am,
It's clear? Okay. Okay, so fine. I think a good number of you have indicated you're clear. What about Divyansh? I've not heard from Divyansh in some time.
Yes, ma'am. It's clear.
It's clear? Okay, great. All right, so what I just did is for the same example for whatever example we took, right, for this robotic car, I've just implemented a value iteration process. So, okay, so I don't know if I told you the name of this algorithm. So this algorithm, this way of doing it is called value iteration. Okay, so let me just write it here. Okay, so this is called value iteration, and it's a famous algorithm. If you have, just if you've skimmed through MDP literature, this is a very famous algorithm. So the idea is, it's the name itself is clear, right? You're iterating over the values with the hope of computing the best values at every point of time, and you are using that to compute the best policy. Okay, so I will just show you like quickly on how it works, the iterations. So here, yeah, is this visible? Is the spider UI visible to you all?
Yes,
Yes, ma'am.
Yes, ma'am.
Yes. Okay. Cool. So here, much of this code is about initializing the MDP and constructing the transition probabilities, rewards, and all that. So I mean, I just hard coded it because it's a toy example. And so the value iteration algorithm I've just written, it's just a very small one because it's an iterative thing, right? So let's just run it. So what I've done is I've set, what's the value of gamma, is it? Yeah, the discount is 0.5. So this is what we used in evaluating a fixed policy yesterday. So the same discount value. And I've fixed the maximum number of iterations as 50. So this K, I fixed the, how far I'm going to go as 50. But you'll see that even 50 is not needed sometimes. I mean, this is a toy example, so even 50 may be less, but for more practical applications, maybe you need more iterations. Okay, and so this is something else. So this is for the next algorithm. I will show you later. This is a different one. Okay, so I will just run the value iteration algorithm. Okay, so let's just run it. Yeah, so it has converged after about 15 iterations. Okay, it's not taken too much time. So what I've also printed is at each iteration, I've printed the best policy so far and also the values of the policies. So let's just look at the values of the policies first. Okay, so it started off like this. The cool state had, a 4, 3.5, and 0. So this is the values of actually V1. Okay, so I just called it iteration 0, but it's actually V1. Okay, and so then in the next iteration, there is a change in the values and so on. Every iteration it's changing. And I've actually stopped, with a convergence test. So I've converged if the values are if you take the norm of this. I mean, this is a vector, right? The values that's a vector. So if the difference from the previous iteration is less than 10 power minus 5, I've just quit. Okay, I'll just come out. So that's why though I gave 50 iterations, it stopped with 15. Okay, and so these were the values. So you can see that it has converged, right? All the states have this value. And, these policies, actually, it's not something that I have to compute in between, but I've just computed it just to see what's going on. Okay? And so at the end of this, I should compute the best policy, and actually turns out to be the same one. I just didn't print it here. Okay. So one thing to note here is, yeah, it has taken about 15 iterations to converge. For real problems, it could take more. But the interesting thing is that the policy, right? At each step, if you compute the best policy, that has converged very quickly. In the first iteration itself, you got the best policy, right? But you are not sure whether this was indeed the best because the values haven't converged, and that's why you didn't stop the process here. Okay, so that's one feature. I mean, this is just an observation that turns out that in many practical problems also the values take a long time to converge, but typically the policies converge much sooner. Okay, it's I don't think there's a theoretical result which shows this, but this is just something that people have observed. Okay, so that's why there's a motivation for is there something we can do better. So that raised the question of can you make some enhancements so that this computation is speeded up. Okay, because if you look at the value iteration, let's see how long it takes for each iteration, right? So in each iteration, you are computing this value, right? This vk plus 1 star of s, right? So how long does it take? So this you have to do for every state. Okay, so this is something, an update that you do for every state. Okay, and yeah, what would the complexity of this be, of one step, of this step of evaluating the max of the summations, if you have again s states, so s states and a actions, s states, a actions. Something happened to my tab. Okay. Yeah. So first thing is, remember, we have to do whatever operation you're going to do, you have to compute the value of every state. Okay. So there is going to be a factor of s which will come in times whatever how much cost this operation will take, this max over a of the summation. So how much do you think this would take, doing this operation, max over a and the summation? What do you have to do? You have to
Action.
enumerate all the actions, right? So you will have to, first thing is for each action you have to do something. So there is this factor which comes in. Okay, so now we have fixed the action, and we have, what do we have to do now? We have to evaluate this quantity, right? So how much is that?
All possible S dash.
All possible s dash, right? So it's just all possible states, right? So yeah, and these numbers you would have with you. So vk is something that you will have in the vector, so you can just look it up. So there's no more complexity issues which depend on the number of states. So this is actually order of s square a, right? Order of s square a. This is the number of operations in each iteration. Operations in each iteration. Okay. So yeah, so if there is some way we can reduce this cost, then that would be great. So that's the motivation for the next algorithm. So can you think of any other things we can do with this algorithm? Of course, this algorithm is there, but now remember, what we want to solve is these Bellman equations. So does anything strike?
Ma'am, could you repeat what you said?
Yeah, so the iteration complexity is there, right? Order of s square a operations in each iteration. Okay, so we want to bring this down a bit further, maybe through a different algorithm. So, but ultimately we want to be able to solve this. Whatever you do, finally in your algorithm, you should get this pi star and you should be able to evaluate v star, right? So is there some other way to, some other thought that comes? Anything about
space also is.
pardon?
We can optimize space also.
Space. So
I mean,
what? I'm not able to hear you loud enough. Can you just, I don't know if, can you come closer to your laptop?
Hello, am I
or...
audible?
Yes, yes. Tell me, it's
I
better.
am
Yeah.
telling that I think we can optimize space also here. We are using a 2D vector. We can say 2D array. So for each iteration, we will be using only two arrays. So we can optimize space here also.
Yeah. So space. What is the space complexity here? Like.
It will be mod of s square.
Actually, you don't need s square, right? Actually, you don't need to evaluate this particular thing. I mean, you can just compute. I mean, what you're doing here, like, let me go down. So what you're doing is we're just computing one vector, right? Of course, these things you have to store it, or somehow you should have a way to retrieve it. But ultimately, our extra storage space is coming only because of this one vector, right?
Oh, okay, ma'am.
So the space is already optimized. I mean, of course, this is minimum information that you will need, and that you already are saving only that much. Okay. So the main thing is with right. So the main thing is with respect to time. Okay. So maybe if you, yeah, can you think of some other possible iterations or other possible way to solve these?
Ma'am, would here we are taking V, so instead if we can use Q, would that reduce it by?
So Q, yeah, so actually V is essentially the same as the Q itself for the next state. It's just we're writing it in a way to separate things out. But here also the Q will need an internal call to the V stars themselves, right?
Yes.
So, um,
Ma'am, we can
yes.
do policy iteration.
Okay, you already know policy attrition. Who is that?
Sanjay, ma'am.
Who said Sanjay? Okay. Yeah, it's exactly I was going to get into policy iteration. So, do others know policy iteration? If you know it, then yeah, you know it. But is this something that you all know already?
No, ma'am.
No,
No,
okay.
ma'am.
So, Sanjay, you did some project or something on MDPs or RL or something?
Yes, ma'am. Like we did a group project last sem.
Okay, okay, okay. Yeah, so that's great. So Sanjay knows all of it. So maybe I'll just explain what the algorithm is. So yeah, it's not very obvious like first time you see it that something can be done because idea is a little different. So I just asked, okay, in case it strikes somebody and you already know it. Okay, so here, what are we doing in value iteration is that at every step you're trying to go towards the best. You are thinking only of the best policy in mind, and all your iterations are written keeping the best policy in mind. Okay, but you can do something else which is slightly off in the sense that you saw how to evaluate a policy, right? Like in the last class we saw how given a fixed policy you can compute the values of that state, of each of these states. So one other possibility is to go in terms of the policies. Okay, so you start off with some policy and see if you can construct a better policy, right? Because if you see the number of policies, that is always going to be a finite number. It can be large, but it's going to be finite. And since we have seen that, in numericals, we see that, the policies typically converge faster. Even if you're doing a value iteration, the policy converges sooner. So why not start off with some policy? It can be a lousy policy, but find some way to keep making this better and better. Okay, so that is the idea in this other algorithm, this alternate algorithm, which we'll see now. So that is called policy iteration. My tab is acting like a random agent now. I think I have to also become a little bit like a robot. Okay, policy iteration. Yeah. Okay, so yeah. So what, like I said, the idea is you fix some policy, fix a policy, get the value. So the policy is pi, and with this, you compute the value of v pi for every state. Now, try to get a better policy. Okay, this is the essential idea. And you do this iteratively till the policy itself converges. Get a better policy. Okay, so I'll call this iteration I. You're doing the policy is pi I. Okay, so you compute v pi I, and then you get a better policy pi I plus 1. So I am putting it here, right? Okay. So this is the idea. So yeah, so there are different ways. Actually, we saw one way to evaluate a policy. So yesterday, what we saw is you can solve, a set of linear equations right? And that's how we solved, V pi. That's how we got the values for a fixed policy. So that is one way. Now, typically, what people do is, you can also go with an iterative way to evaluate a policy. Okay, so policy evaluation. So that is this step. The first step is policy evaluation. Just give me a second, okay? I'll just disconnect my tab and just try once more. It's behaving very erratically. Yeah, it's better. Okay, so so policy evaluation is this first step. So this is first step, and this is the second step. So policy evaluation, like one way was method one was to solve a set of linear equations, solving a linear system. Now, there is also an iterative method to do this. So sometimes people also go for this, like for larger problems, sometimes you can do an iterative way, so that even the iterative method converges. But yeah, there's nothing like you have to use only this or that. It's up to you. Whichever you want, you can use, depending on what works. So let's just see this iterative method. The idea is very similar to what you did in value iteration, but just that you don't have this max step. Okay, so again here it's like you start off with there's a policy pi that is given to you, and you do this truncating idea. The time steps, you have like k time steps left. So v0 of s under pi, that is 0. Okay, and again, so let me just write it properly. Vk of pi is the value of state s. If you have k more time steps, and you behaved as per policy pi, k more time steps and behave as per policy pi. Okay, so that is the difference from the previous vk star. Okay, because there what we said is we are going to behave optimally always, and you behave optimally. So this was where it differs from vk pi. Okay, now you're going to behave as per policy pi. Okay, so initially there is you have no time steps left, so the value under any policy is 0, and at every time, so at the same procedure goes on. So at the k plus 1th time step, what you're going to have is you have all these possible states that you can get to, and the action you're going to take is pi of s. Okay, and you're going to reach s dash, and then you have the reward, the first reward in the first time step, plus gamma times vk pi of s dash. Okay, the same procedure, right? Like you start in s, now you're going to take pi s, and there'll be some intermediate agent, but there'll be different possibilities. You'll hit s dash, and this is at the k plus 1 time step, and here you had a utility of vk. So what are the possibilities? It's just an expectation computation, right? So this is just the expected value over all possible states. This quantity, reward of s pi s dash plus gamma vk pi s dash. Did I write gamma vk pi s dash? Okay, and you keep on doing this, and by the same logic, this will also converge. Okay, because finally, what is going on is everything is getting scaled by gamma, right? And as you go further and further, all these terms are good terms, but The V0 is where there could have been some mistake, right? And so that gets scaled like by a very small number. So this quantity is eventually going to converge. Okay, so this is the policy evaluation stage. Okay, and the next is just to get a better policy, right? So this is like you assumed you have a policy pi and you computed the value. Now, how do you get a better policy? If you are finally you have, so let's say V pi of S is given to you, right? What would be, how would you compute a better policy? What should the best action, if you have some value function V pi, and then you're trying to say, okay, with these numbers, I have to do something, I have to do something good. Okay, so what do you think you could do? What
Argmax.
action should you take? Argmax, right? Exactly. So that's the policy extraction stage. So I'm just telling you, I mean, I don't really care about these terms, but I'm just telling you because, if you read some textbook or, some other references, they will use these terms. So I just don't want you to get lost when you see it. Okay. But anyway, so what you're going to do for the next policy. So here you had the policy pi I. Okay. So this was the iteration. I'm just zooming in into each of these steps. Okay, so in policy evaluation, you started off with pi I and now you want pi I plus 1. Okay, so what you have at the end of iteration I is V pi I. Let me just write it like this, V pi is at iteration I. Okay, iteration I. So this is an outer iteration. Okay, so let me, so this is the main algorithm, right, for policy iteration. So for I equal to 1 to something like, as much as it takes to converge, then you have this is policy evaluation. And there inside there was some more iterations. Okay, so don't get confused with two sets of iterations. Okay. So here what I'm saying is V pi I is about the outer iterations. Okay, at iteration I, there is this value V pi I that you get. Now you need pi I plus 1. Okay, so pi I plus 1 of S. It's just, you just take the argmax, okay, with whatever you got from V pi I. So here again, the possibility was one of these expectations, right? One of these actions would give you a better value. So S, and you have to find what is pi I plus 1. Okay, so yeah. So what can you tell me? Can somebody tell me what this value is going to be? You've done a lot of these computations now, so hopefully you're used to it. It's also an expectation, right?
Ma'am, it
you're all
would be direct argmax of
yes.
V pi I of S, right?
Not V pi I. So remember, like if you take some action, there is this Q agent which comes in between and does something else. So you get V pi I only here in the next part, right? The thing is, you don't know where you are in the next step once you take an action, right? Argmax of, can you speak louder? Who is it? Who is speaking? Somebody said something. Okay, it's basically the same idea, right? I mean, you just take the summation over all possible states. You have this quantity times R S A S dash, the single step reward, plus gamma times, now here you use V pi I of S dash. Okay. Bad board work, but okay, so you just it's essentially the same steps, okay, but just that over here you use V pi I from what you computed already for the previous policy, and in this way you keep making the policy better and better. Okay, so this also has a proof on why the policy will get better. So there's also a result here which says that, remember, like first we saw that, not every pair of policies are comparable, right? But here, if you do this policy extraction, it turns out that at every stage you will get a better policy for all the action, for all the states. Okay, so, but anyway, we are not going into the proof of that because already all of you are like very quiet. Okay, so I don't want to bother you with more details like this. Okay, so maybe I hope the difference between these two algorithms is clear. I just wanted to also show you policy iteration on the same example. Maybe, okay, can I take some more time, like maybe 5 minutes?
Yes.
Who is the class rep? Yeah. Okay, class rep is not responding anything, so I will assume that I can take 5 more minutes. Okay. All right. So, yeah. So let's just print. What I've also done is I've tried to compute the times. Okay, for each thing, for each algorithm, what's the execution time? Also, I've computed. So let's just run both. Okay, so the last part is the policy iteration. Okay, so what I did is I started off with a bad policy. So you have to initialize some policy. Okay, you can choose randomly. So here what I've done is I've purposely chosen a bad policy. This was the fast policy, and yesterday we evaluated its value, right? So now I've used this iterative method to evaluate. So in the first iteration, this is the inner set of iterations. There have been about 11 iterations, and it's finally got this value. So this tallies with what we computed yesterday, 3.5 and minus 5.5. Okay, and so this was the first policy we started off, but again now this has also converged. It has got the best policy after this. Okay, and yeah, so afterwards it's just about converging to the right value. So that's why it's just taken a few more iterations. So here again now the policy converged soon. So let's just, so in this, okay, this is a toy example where both value iteration and policy iteration converge to the best policy quickly. But in terms of times, evaluation times, there's a difference. Okay, so let's just see that. So the value iteration policy, yeah, this is the time it takes. The value iteration algorithm, this is a small value, like 0.005 seconds. And let's just see how much policy iteration takes. Yeah, so 0.002. So of course, these are toy problems, but if you see, there's like a 50% improvement, right, for policy iteration. So that's happening mainly because, you're avoiding doing a max step at each iteration. So doing this max kind of operation at each point, that is what is causing some overhead, and you're improving because of that. But at the same time, you are converging. Though the inner iterations, it takes some time, but it's still much faster. Okay. All right. So this is what I wanted to illustrate to you all. So I would encourage you guys to just try to implement both these algorithms once yourself on this toy example. It won't take you too much time because this maybe will take about half an hour or 40 minutes, or it takes less than an hour to implement. The reason I'm asking you to do it is, if once you implement, then only you realize whether you've clearly understood it or not. Okay, of course in your labs I think value iteration will be there in the Berkeley labs, but I think policy iteration is not there. We go to reinforcement learning, some other concepts. Okay, so yeah, please try this out, try implementing yourself. So I will stop here, and if there are any questions, I'll hang back. Otherwise, thanks everyone. Okay, and yeah, I think some of you also would have got an email for the labs today. Sorry, I missed telling you. So some labs, some of the groups we are conducting vivas today, the particular groups would have been informed. So please show up at the time that you've been told to. Okay, I don't want others to show up in those time slots. Okay. All right, so thanks everyone. Yeah. Could you please share the code? Yeah, sure, I can share the code. But I would encourage you to just try it once yourself without looking at the reference. Okay. So, or maybe let's do it. You just try it yourself. If you're finding it difficult, then let me know, because I don't want you to just see it, and you should be able to write the code from the iterations. Okay. So just try it once yourself. If it doesn't work, let me know. Yeah. Yeah. Thanks, everyone. Yeah.